Hello, everyone. My name is Hamidreza Shabgard. I am an assistant professor at the School of Aerospace and Mechanical Engineering at OU. The project I am presenting today is an ongoing work on treatment of produced oil and gas produced water, funded by ARPA-E. The PIs are Dr. Parthasarasi, Dr. Kai, and myself, all from AME OU.
Hamid, before you go too far, can you make your screen full screen?
I thought I did. Let me see. Oh, is it good now?
Yes, thank you.
So as you see, as the title suggests, the way we treat the water is using the freeze-desalination technology. And here is the outline of the work. A brief overview of the produced water problem, introduction to OU's concept, then process modeling, computational modeling, and experimental work. And finally, the most important part is probably the thermoeconomic analysis. So I'm not going to talk too much about the introduction because I assume everybody here is pretty familiar with the issue of produced water. In summary, there are 9 to 10 barrels of water per barrel of oil average in the US. So there is a lot of water to deal with. And this water is highly contaminated. And it's a challenge for the producer to get rid of. A very famous picture here from Whale paper, the current practices in handling the oil and gas produced water. As you see, most of it is injected for enhanced oil recovery and then deep well injection to just dispose of the brine. And this is the current practice for impoundment, hauling, and disposal well. And this is a very relatively expensive process for the producer and can cause a lot of challenges, economic and environmental. So before looking into the details of the technology that we are working on, it's good to know the existing technologies for treatment of brines and their range of application. The technology that we pick strongly depends on the TDS of the brine that we are dealing with. As this figure shows here, at a smaller brines, ion exchange and electrodialysis systems are common and can have potential advantage in terms of economy and quality. But in the mid-range, like seawater and almost up to the limit of 70,000 ppm, reverse osmosis is the dominant technology in the world. About 70% of the entire desalination in the world is using reverse osmosis. It's a mature technology, very cost-effective, very hard to compete with. But this technology's upper limit is really around 70,000 ppm. And that's exactly where the TDS of most of the oil and gas produced water starts. And for TDS larger than what reverse osmosis can handle, there are typically thermal methods that include evaporation and then freeze desalination. So freeze desalination can potentially be advantages over evaporative methods because of the fundamental difference between evaporation and freezing process. To freeze 1 kilogram of water, we need about 1/7 of the heat that we need to evaporate the same amount of mass. So if we can tap into this potential and take advantage of the lower energy consumption for freezing, we can save a lot of energy and money for treating these highly concentrated brines. So when it is a well-known fact from old times that when you freeze brine, the ice that you obtain is at a much lower TDS or salt concentration than the original brine. So if we freeze and then we melt it, we can reduce the TDS or even purify the water just by freezing and melting. There are various technologies for freeze desalination that can be categorized as a type of freezing, like direct contact freezing, vacuum freezing, and indirect contact freezing. The entire idea behind this freeze-desalination is this is your starting point, like brine at room temperature. You freeze it first. At the first step, you have just sensible heat cooling, and until you get to the eutectic line. At point B, further cooling would increase the concentration of the brine by separating the pure ice in the form of the pure water in the form of ice crystals. So you separate ice crystals, and the remaining liquid would get more and more concentrated until you get to the eutectic point. If you further cool down the system at eutectic point, all your brine would solidify, and you would have a mixture of ice and salt hydrate. So this is an overview of the existing technologies. Vacuum freeze basically works based on the principle that if you lower the pressure of the vapor, the saturation temperature would go down to a point where you can actually freeze the water. It has good heat transfer, but the compressor work that you require to create the vacuum is very high and usually makes it implausible from the economic point of view. Then we have direct contact freeze. In this method, people inject refrigerants into the brine. The refrigerant comes in as a liquid, and by absorbing heat from the brine, it evaporates, and at the same time, the brine would freeze. This has a very, very good heat transfer, but usually the refrigerants used in this technology bond with water and form some chemical bonds that lead to formation of compounds that basically deteriorate the quality of the water that you obtain from this technology. And finally, we have indirect contact. In this method, we run the coolant through a channel, and that coolant is separated from the rest of the brine by a solid wall, and ice forms on those solid walls. The good thing about this is the ice quality is pretty good because we prohibit the mixing of the refrigerant with the water, but almost always there is an attachment of the ice to the solid surfaces, and separating the ice can be pretty challenging. And over time, the quality of the speed of the ice formation drops because as the ice layer grows, it forms a thermal resistance and it slows down the entire process. So here is the technology that we are working with. The basic idea behind this technology is that we use an inert liquid, we refer to it as ICL, to act as an intermediate cooling agent between our refrigeration system and the brine. So we have this liquid that is immiscible with water and will not freeze until -80°C. So we cool this liquid, we inject it directly into the brine, we spray it into the brine, and by the direct heat transfer that occurs between these tiny particles of this inert liquid and the brine, we form ice. So this has the benefits that direct cooling methods offer, that is large heat transfer, and at the same time, since there is no solid surfaces between the refrigerant and the brine, the ice is just suspended in the solution, and it's much easier to separate. And we do not use any chemicals in this process, and the entire system works at almost atmospheric pressure or very close to atmospheric. That makes the process very easy to manage. So to calculate the actual energy consumption of the system, we have to do some process modeling. And this is a heat transfer and chemical problem combined. We cannot just have a heat transfer model and account for the complicated chemistry that happens in the brine. So we had to use different softwares for this process modeling and actually understand the energy consumption of the system. In summary, the process is consisted of 3 segments. First, freezing, and then a separation, and finally melting or dissociation. Melting is related to the ice, and dissociation is for the salt hydrates that form. So as you can see here, brine enters the freezing compartment. The cooling liquid is the purple line here. It circulates in a separate loop. It cools the brine and freezes. This slurry of the cooling liquid and unfrozen brine and ice is introduced into a separator, and ice, unfrozen brine, and the salt hydrates are separated, and each of them follows either melting, dissociation, or recirculating back to the freezing chamber. So for the model should be able to treat the actual high TDS brine that we deal with in oil and gas. It should be able to model a continuous operation, large scale operation. It should be able to provide large heat transfer coefficient. We want a system to have very small number of moving parts, and this separation process should be easy and manageable, and the overall cost of energy should and the production rate of ice should all be optimized, and there should be no environmental concerns with the chemical, with the liquid that we use for this process. So the tool that we developed for modeling this process consists of two softwares, Aspen Plus and OLI. So OLI is a software that is very, very good at taking care of the chemistry of the solutions, but it cannot do the process modeling. So we combine OLI with Aspen. Aspen has a large library of all different process modeling units. You can connect them like what you see here, and you can link it with OLI to take care of the chemistry in the freezing process, in the melting process. And by developing a model like this, including all the components that exist in the system, we can determine how much energy we need to complete this process, what fraction of the input brine we can recover as purified water, and what fraction of it should be rejected as unfrozen brine. And these are the samples of the brines that we used. We obtained this from Oklahoma Geological Survey. As you see, we account for the actual composition of the brine with all the different ions existing in the brine. So these brines are created with the same exact composition that you see here in the OLI and then introduced into the Aspen model. We also analyzed an alternative design. We refer to it as a two-stage design. It's practically the same, but with some modification to further lower the energy consumption of the system. We also did some computational modeling to understand better the freezing process. I'm not going to talk too much about this. I just briefly walk through it. We did to identify like what type of spray freezing we need for achieving the required heat transfer in the freezing chamber. We did some computational modeling using the Eulerian-Lagrangian approach. These are some details of the Eulerian-Lagrangian approach and the interaction between the solid particles that are formed upon freezing of water and the continuous phase that is our inert cooling liquid. The model also accounts for the heat transfer, for the phase change that occurs for the brine from liquid to solid, and that is handled using the enthalpy method. And this is the domain that we considered. So we injected the cooling liquid and the water at the same time, and freezing occurs in this chamber as the flow goes upward. And these are the trajectories of the water particle. And the main purpose here was to identify at what spray size, what would be the freezing time. And results show that freezing time is not an issue. For all the cases that we simulated, we realized that the majority of the water that was injected was frozen in less than 2.5 seconds. So the average time of freezing was about 3 seconds, and that is pretty manageable. And the next part is design and fabrication and testing of a prototype system. So for this, we have a 3-ton refrigeration system, and we connected this refrigeration system to the freezing system that you see here. So this is our refrigerator. And this is the interface between the refrigeration system and the desalination unit. We have the brine injected into this column. This is our ICL tank. We pump it through the heat exchanger. We cool it by heat transfer with the refrigerator. We introduce this cool liquid into the freezing chamber. At the same time, the brine is injected. They mix in the freezing chamber. Freezing occurs. The slurry is introduced to a separation column. Ice and ICL leave the separation column from the top, and unfrozen brine leaves from the bottom. And then we have a filter system that separates the ice from the rest of the liquid. The ice accumulates on the screen, and the liquid is returned to recycle. Another view of the experimental setup, the heat exchanger. This is the grinder unit at the bottom of the freezing chamber, the freezing chamber itself, the settling tank, and the pump. So the whole flow loop works with only one pump. This ice grinder unit directly under the freezing chamber prevents the clogging. Clogging is an important issue in our system. And with introducing of this grinding system, we could solve the clogging issues very effectively. The flow control was found to be very easy, and we could easily control it with either a VFD that controls the speed of the pump or the valve that we have in the system. So this shows some results of the freezing process. There is a video here and another video in the next slide. I try to show them really quickly. The brine we used for this test was a NaCl water mixture with a TDS of 50,000. The temperature was maintained between -8 and -13. And you can see the results of freezing here. So you see the droplets. These are water, and as the water goes down, it freezes. Once we start to operate the grinder, a swirling motion is introduced that creates a very, very effective heat transfer and prevents large ice chunks to be formed. So the ice that left the grinder unit was between 200 and 500 micrometer. Another video showing more details of the freezing process. So this is our freezing chamber. The grinder is currently working, and that's why you see the swirling motion. And at the outlet, you see the ice and ICL slurry moving to the next step, that is the separation process. And the next step is separation. This is a pretty simple system. We basically have a trough made by bending a plexiglass sheet, and on top of it we have a filter, and the slurry is just released on the surface of this filter, and the separation system is oriented with a relative inclination angle. So ice stays on top of the filter, the liquid penetrates through, is collected by the trough and introduced into this ICL bucket. The ice would be collected from the top of the screen. We have a newer version of the separation process that is in the process of filing for patent and could not be shared here. So there is another video that shows the separation. I just skip it. And this is the result. This is the sample of ice that was collected before melting, and after melting, you see the bottom is the water, and on top this is the cold liquid, the inert liquid that we use. So the ice carries some ICL with it because it attached to the surface. It's usually 60 to 40%, the ratio of water to the ICL. And all we need to separate this is let it melt, and then they separate by gravity. And finally, we used the results of the process model with the input from the experimental and computational model to approximate the cost. As you see, it's a breakdown of the cost associated with this technology. The majority of the cost relates to the electricity consumption of the system, about 50%. The next major cost component is labor and maintenance, about 30%. Brine disposal accounts for 13% of the total cost of the project, followed by the refrigeration cost, the inert liquid or the ICL price, and some other smaller cost components like installation, site preparation, and so on. And we did some parametric studies on the levelized cost of water under various design operations, including the heat exchanger efficiency and the separation effectiveness, and as a function of the TDS of the input brine. For a TDS of 100,000, the average price was about $0.50. And then for 200,000 ppm, about 60 cents. And the highest TDS that we considered was 300,000. And as you see, the price was around 70 cents. So that's all. And thank you very much for your attention. I would be happy to answer any questions if there are any.
Great, thank you, Hamid. Great presentation and a very interesting research and work that you're doing there.
Thank you.
We do have a question in the chat that says, seems like the water used in the system is pretty clear, but in produced water, there is oil and grease. Does this system require pre-treatment of the wastewater prior to freezing?
So that is a good question, and that's right. As I said in the experimental part, the brine that we used for this experiments was just, we made it in the lab. We mixed table salt with water to make this composition. This prototype has been completed recently. So this was the first stage. We have obtained actual produced water samples from Lagoon, and we really appreciate their help here. And we are planning to use it. We do not exactly know what happens if we have oil in the system. The fundamental principle of operation is not affected by the presence of oil or any other organic components in the system, but in practical aspects, we have to test and see what happens.
Great. We have a hand up, Maria Okpala. You want to ask your question?
Yes. I am curious to know what the removal efficiency is in the 50,000 ppm, and how can you measure the amount of brine that has been removed?
Okay, thank you very much. Another very good question. So the next phase of this project, as we have scheduled with the ARPA, would be detailed characterization of the water that we recover from the system. But at this stage, and that would require equipment that we are buying at this point, what we did, we just, the water that we recovered, we boiled it, and we measured the mass of the remaining solids. And for this 50,000 ppm, the mass that we collected accounted for a TDS of between 1,000 and 1,500. That's very rough. We just obtained that by boiling the water and measuring the solid mass.
There's another question in the chat, this one from Dr. Khaled Salam. So does the cost change as the ambient temperature drops in the winter? And if so, by how much?
Very good question. Yes, as we said, the main cost component here is the energy cost, and energy cost directly relates to the COP of the refrigeration system. And the COP of the refrigeration system depends on the cooling temperature. So in this work, most of the cooling of the condenser is by the ice. So the ice that we generate, we use it to cool the condenser, but there is an extra cooling required that would be relying on the ambient temperature. So in the winter, as the lower temperature outside actually would help the compressor to lower the compressor work and lower price. In the summer, it would be the opposite effect. All the simulations here were assuming that the outside temperature is 20 degrees. we have not done like a detailed analysis of the effect of ambient temperature and how it affects the total energy consumption and the cost.
Okay.
Very good question. Thank you.
I see Kyle Murray has his hand up. Kyle, do you want to ask your question?
Sure. This is more of a philosophical question. I know in the past that you and your research partners at OU have focused on thermal treatment technologies that involved heating the water and evaporating or distilling essentially the water.
Mhm.
Why have you shifted to cooling the water now? Is it more of a technical advantage, or is it more of an opportunity to fund a new line of research? Just curious.
It's both. So there, the main motive for looking into freezing was potentially lower energy cost. As I said, for per unit mass of water, you need 1/7 of energy to freeze than to evaporate. But there is a very important technical problem with evaporating. For produced water, as somebody else also mentioned, there is a lot of hydrocarbon in the water, oils, all sort of hydrocarbons that evaporate before the water evaporates. So when you evaporate, all these hydrocarbons would be in your vapor. And when you condense, the water that you recover is mixed with all sort of, it's like a refinery, basically. You evaporate the water and you recover all those volatile compounds mixed in your water. So you have, you do not really treat anything. Your water is, you get rid of the solids, the salts and stuff, but a lot of hydrocarbons would remain in the water that makes it practically unusable.
And this avoids that problem.
Yes, it is only a freezes water. Yeah.